Hi, everyone. It is really great to be here to have Casey's thesis now. I'm so excited about this. Casey and I go back a very long way because he did do his undergraduate here at Stanford in Earth Systems and with a focus on economics and the anthrosphere area, and was working in the marine policy area. So Casey and I had many, many conversations when he was an undergraduate and got to know each other well. He went off to the Bren School and did a master's at UC Santa Barbara. And luckily, we were able to pull him back to Stanford into the E-IPER program. And I think what really distinguishes Casey among the other students that I've worked with and other students in the program is, first of all, how much commitment he has actually put into the economics track, which, as many of you know, just requires 1 million prerequisites and a lot of hours and hard work. Several of you have gone down this road, and Casey did do his exam in economics and development economics and passed, and has really showed a commitment in that field. So that's been very fun to work with, since he does have then a broader expertise in the scientific area. If you'll hear about his thesis now, there's 3 different chapters, and you will see actually each of these different papers could be a complete thesis. And in fact, he's done so much work on each of them. They are kind of like 3 theses. So that's another thing to note. And then the final thing really on the personal side is just how much fun it is to work with Casey and to engage in conversations. And his depth of knowledge, both in the theory as well as the empirical methods, is so fantastic. And then with me, he's really dived into field-based research, and that's been fun and very time-consuming as well. But what he has gained, insights that he's gained from the field and how he has connected that to both the empirical and theoretical analyses, I think is really special. And you'll have fun listening to this, this defense. Casey is going off to Paris with a job. I certainly plan on visiting him, and I'm sure many others are lined up. He's going to be working with Karen McClure, who is chairing the standing panel for the impact assessment for the CGIIR, which is the Consultative Group on International Ag Research. And this will entail work on agriculture, climate, development, the areas that he has really specialized in with his thesis, based at the Paris School of Economics. And so I look forward to that next adventure with you, because you're not going to get rid of me, Casey, and I'm sure that holds for the rest of your thesis committee members. So I'll turn it over to you now to start your defense. Thank you.
Well, thanks everyone for being here, and thank you so much, Roz, for that wonderful introduction. It really is a privilege to be able to talk about my dissertation work with everyone here today. So the title of my talk is Climate, Agriculture, and Economic Development, Theories and Methods for Agricultural Productivity Analysis. And so why is agricultural productivity an important sustainability issue? Well, a first order reason is that the environmental footprint of agriculture is massive. Agriculture accounts for more than 25% of global greenhouse gas emissions, occupies more than 50% of the habitable land surface of the planet, and consumes more than 70% of total freshwater withdrawals in any given year. It's also the primary driver of deforestation and biodiversity loss worldwide. So if we as a society want to continue to feed and nourish our growing and increasingly wealthy world population, we're going to need to figure out how to produce more food and agricultural output using the same amount or fewer agricultural inputs. And this is by definition increasing agricultural productivity. The second reason that agricultural productivity is a sustainability issue is because of the close relationship between agriculture and poverty, which is highlighted in the figures shown on this slide. So on the left, I'm showing the share of the population that lives on less than $3.10 per day. And on the right, the share of the labor force in each country that is employed in agriculture. And as you can see, areas with high incidence of poverty are also those where the majority of the labor force is employed in agriculture. And so this relates to sustainability because if we think about sustainability as an issue of the equitable sharing of resources between present and future generations, well, then that same concern for distributional equity should also motivate us to be worried about income inequality in the present. And so increasing agricultural productivity is not only a means of conserving resources for future generations, but also of promoting economic opportunity for those who are least well off today. And so the idea that agricultural productivity is important for poverty reduction is not new. This has been part of the global development agenda for the better part of the last century, but there remain open questions about how to effectively reduce poverty through agricultural development. And some of those are highlighted in the figure on this slide, which shows cereal crop yields in a number of countries and regions over the period 1961 to 2018. For example, one open question is, why are there such large yield gaps or differences in productivity between rich countries like the United States and lower income countries in the developing world? Another open question is why in some regions, in particular those where poverty incidence is high, has productivity growth been so limited over the past 70 years or so? Another important source of uncertainty about the future of economic development is in agriculture is, of course, climate change. So this is a figure from a recent report by the IPCC, which shows predicted changes in cereal crop yields by the end of the century, as modeled by an ensemble of global gridded crop models, or GCCMs. And the important thing to take away from this figure is that climate change is predicted to have significant negative impacts on crop yields, in particular in many low-income countries in Africa and Southeast Asia, located in the global tropics. And this introduces another layer of uncertainty about how to promote poverty reduction through agricultural development. For example, are climate mitigation and adaptation strategies focused on agriculture also going to impact poverty outcomes? And if they do, how effective are climate-based agricultural development strategies at reducing poverty relative to traditional or non-climate-based strategies? So these are open questions, but one obvious prerequisite for being able to answer them is being able to measure the impact of climate change on agricultural productivity outcomes accurately. And so in my dissertation, I addressed the interrelated themes of economic development, agricultural productivity, and climate change in 3 distinct chapters. In my first chapter, I study patterns of productivity observed in household survey data from smallholder farms in sub-Saharan Africa, and study how those patterns of productivity are affected by measurement error in those data. In my second chapter, I advance a new method for quantifying the impact of climate change on agricultural productivity outcomes. And in my third chapter, I look at how climate affects the organization of industrial activity, focusing on a case study of the palm oil processing sector in Ghana. So I'd like to discuss each of these chapters now briefly in order. So starting with chapter 1, the motivation for chapter 1 is that despite increases in the availability of satellite imagery and other data sources, household surveys remain the primary way that we measure and study productivity dynamics in developing country agriculture. However, recent studies have also pointed out that many of the survey-based metrics that we use to study productivity recorded in these surveys may contain measurement errors. And so a research question that we can ask is, how does measurement error in household survey data affect the way that we evaluate the effectiveness of different types of development interventions that are targeted at increasing agricultural productivity? And to address this question in this study, we're going to quantify patterns of productivity observed among smallholder farmers using household survey data, and then advance a new method for quantifying the extent to which these patterns are affected by measurement error in the survey data. So what do we mean by patterns of productivity? One important pattern that we look at in our data is called productivity dispersion, which we can think of as measuring the size of the difference between low and high productivity producers. And productivity dispersion is important for thinking about development interventions because a number of recent papers have suggested or hypothesized that simply reallocating inputs of production, such as land, from low to high productivity producers can produce significant gains in aggregate agricultural productivity in developing countries. So to fix ideas, we can think of this simple stylized example where we have two types of farmers in an agricultural sector. We have low productivity farmers and high productivity farmers. And in scenario one on the left, each of these two types of farmers control 50% of the total land in a country or in this agricultural sector. And then an intervention that reallocates land from low to high productivity farmers is represented in scenario two. And so if we just give 90% of the land to the high productivity producers, we see that we increase average yields from 6 to 9.2 metric tons. What should also be clear from this example is that the gains associated with reallocating land in this way are a direct function of the size of the difference in productivity between high and low productivity farmers. So if high type farmers achieved 15 metric tons per hectare in yields, then the gains associated with reallocation would be even larger. Okay, so we're going to measure productivity dispersion using data from the World Bank's Living Standards Measurement Study Integrated Surveys on Agriculture, in particular the LSMS ISA surveys from Tanzania, Uganda, Nigeria, and Ethiopia. And across all of these 4 countries, we're going to see data from more than 12,000 farm households and nearly 100,000 agricultural plots. And one of the key characteristics of these data, or one of the really cool characteristics of these data, is that they contain super detailed information on agricultural inputs used in agricultural production and output produced for individual agricultural plots. So we're going to be able to measure productivity at the plot level, and that is going to be the foundation for our analysis. Another interesting feature of these data is that they contain multiple measures of inputs used or output produced on the same plot. That is, multiple different survey methodologies were used to measure the same thing on the same plot. And that's going to be useful for our approach to quantifying the effect of measurement error. Okay, so the notion of productivity that we're interested in this study is called total factor productivity. And to understand total factor productivity, it's useful to start with a simpler, more intuitive notion of productivity, crop yields. So crop yields, we know, is just the ratio of how much crop output is produced given the amount of land input that is used. So this is a single factor measure of productivity. It is a measure of land productivity. And by contrast, total factor productivity is the ratio of output to a weighted product of all the different inputs that are used in agricultural production. So land, labor, and capital. And if you remember your log rules from algebra class, you'll know that we can write this expression for TFP as a difference. If we take the log of this expression, we can write that as the difference between log output and the weighted sum of log inputs. And this is useful because it lends itself quite directly to a regression-based approach to measuring TFP. In particular, we're going to measure TFP as a residual from the regression of log output on log inputs plus some additional controls. So in the equation shown on the slide, this residual term EIT is going to be our measure of productivity on a particular plot. Okay, so our first empirical result is that if we measure productivity in this way, and we compute productivity dispersion without doing anything to account for measurement error, then productivity dispersion looks very large. So our preferred measure of productivity dispersion is called the 90-10 ratio. It is the ratio of the 90th to the 10th percentile value of the distribution of our estimated productivity of residuals. And this figure shows the estimated 90-10 ratios for each of the 4 countries in our sample. And these values imply that 90th percentile farmers appear between 7 and 10 times more productive than 10th percentile farmers, which those are very large differences. Okay, but we know that, or we're interested in understanding the extent to which this sort of naively measured productivity dispersion is affected by measurement error. So how are we going to do that? The essence of our method for correcting for measurement error relies on the existence of multiple different survey methodologies that were used to record crop output on the same plot. So for a subset of plots in our data, we have a measure of output that comes from farmer reports, where survey enumerators simply asked a farmer how much output was produced on a particular plot. And also on that same plot, enumerators participated in an exercise called crop cutting, where they conduct a partial harvest of the plot, usually within a randomly selected sort of 2x2 section, harvest the crop growing within that section, dry it and weigh it. And so this provides a secondary independent measure of crop yields on the same plot. Now, both of these we can consider to be noisy measures of crop output insofar as they might both contain measurement errors. Farmers might struggle to recall exactly how much crop output was produced on a particular plot if a survey was enumerated weeks or even months after they harvested it. Record keeping is often imprecise in some countries where these surveys are enumerated, and so there might be measurement error in those estimates. Similarly, crop cuts are a sample within a plot and a random sample of yields within a plot, and therefore may not be representative of the productivity of the plot as a whole. So using these 2 noisy measures of crop output, we're going to compute TFP using each one. So we're going to compute TFP using our farmer reported estimate of crop output, and also separately using our crop cut based estimate of crop output. And then we're going to generate 2 composite measures using these 2 different independent estimates. One is just the simple average of the 2, and the other is what we call the projected composite, where we try to predict farmer reported TFP using crop cut TFP. And what we show in our paper is that the 90-10 ratio of these 2 different composites actually bound the 90-10 ratio of the true TFP distribution that is measured without any measurement error. So the average composite is in a sense too noisy because it combines or compounds the measurement error from the 2 different estimates. And the projected composite is not noisy enough because it is only capturing variation in one measure that is predicted by variation in the other. And so using this approach, we can compute the extent to which measurement error affects the sort of naive estimates of productivity dispersion that we compute if we just use the farmer reported output. And this figure shows how we do that in our data. So this open circle at the top is our 90-10 ratio based on the sort of naive standard farmer reported estimate of crop output. This gray box is the region that is bounded by our 2 composite measures. So we think the 90-10 ratio of true TFP lies somewhere within this region. And so at a minimum, the role of measurement error in affecting the sort of naive estimate is given by the difference between this open circle and the top of the gray box. And if we express that as a percentage of the sort of baseline naive estimate, we find that around 42% of apparent productivity dispersion in our data is actually attributable to measurement error in farmer reported crop output. So that's really large. So to summarize what we do in this paper, first, we show that if you use conventional survey-based measures of inputs and outputs to compute productivity dispersion among smallholder farmers, it looks very large. We then demonstrate a method by which you can use multiple independent measures of output contained in a survey data set to quantify how much measurement error affects estimates of productivity dispersion. And we apply this technique to our data to show that measurement error accounts for about 50% or roughly 50% of naively measured productivity dispersion. And so an important conclusion from this analysis is that potential gains from the type of reallocation development intervention that we talked about at the beginning of this chapter may be overstated. That is, the apparent differences between low and high productivity farmers observed in household survey data may look larger than they actually are simply because of the presence of measurement error. Another important conclusion from this work is that developing survey methodologies which provide multiple independent estimates of important quantities, such as crop production, is a really important way to learn more about the role of measurement error in household survey data. So a sort of recommendation for survey design. Okay, so now I'd like to discuss my second chapter, in which I propose a new approach to measuring the effects of climate change on agricultural productivity. And the starting point for the discussion of this work is the distinction between weather and climate. So weather we can define as a summary of the state of the atmosphere, such as the temperature or the amount of rainfall in a particular place at a particular time. So for example, one measure of weather would be the total amount of rainfall that fell in Piatt County, Illinois, between April and September in a given year. And the figure on the right is showing a summary of the distribution of individual realizations of this weather variable over the period from 1951 to 2017. And this blue line represents an approximation of this distribution, which is given by a normal probability distribution. And so we can think of each realization of weather, each instance of precipitation in each year, as being a draw from this approximated distribution. So weather is a random variable, it has a distribution, and each realization of it is a draw from that distribution. And if we think about weather in this way, then climate can be defined as the set of parameters that define this distribution. So in the case of a normal distribution, a mean and a standard deviation. Okay, now because we cannot experimentally alter the climate as we would in, say, a randomized control trial to understand the effects of climate change, we have to try and infer how climate affects economic outcomes by looking at observational data of weather and climate and economic outcomes. And there have been a variety of methods proposed to do this. First, there are cross-sectional approaches in which you simply look at the statistical relationship between weather and climate directly and try to control for potential confounding factors. There are what are called panel weather models, where you instead look at the relationship between outcomes and weather and control for a richer set of potential confounding factors, and then relate these estimated weather effects to the impact of longer term changes in climate. And increasingly, there are hybrid approaches that attempt to do a bit of both, that attempt to leverage both the variation within units over time in weather and also the longer term cross-sectional variation in things like average weather. But a key motivation for our work in this paper is that none of these existing methods fully or formally recognize the statistical relationship between climate and weather. So the Ricardian approach, for example, just considers climate and not weather. The panel weather model, by contrast, just looks at weather and not climate. And even in the hybrid approaches, there's an implicit relationship between weather and climate that is part of that model, but this sort of formal statistical relationship is not fully recognized. So what we're going to do in this study is first derive a theoretical expression for the effect of a marginal change in climate that explicitly incorporates this statistical relationship. Second, we're going to develop an econometric framework that one could use to estimate this theoretical construct using observational data. And finally, we're going to provide an application of our method where we use data on weather and agricultural productivity from US counties. Now, for the sake of time today, I'm not going to go into our theory or the econometrics of our method right now, but I would like to talk a little bit about how our approach provides some additional insights relative to previous methods. And to do that, it's important to differentiate between three different channels through which climate change can affect economic outcomes. The first one is perhaps the most intuitive: climate as the set of parameters that defines the probability distribution of weather affects future weather patterns. If climate changes, the nature of weather realizations in the future changes, and this will affect the expected value of economic activities that depend on the weather. A second channel is through adaptation. If climate changes, then economic agents might make decisions that are designed to maximize profits given the newly changed or marginally changed climate. So for example, if I'm a farmer and I think that the climate is getting drier, then I may invest in an irrigation technology in order to reduce the effect of drought on my crops. And then a third important channel, and one which has been understudied in the climate impacts literature to date, is the way that climate can affect outcomes by changing non-weather inputs to production that are not actively decided by or determined by the decisions of economic agents. So again, the agricultural example is a useful one. Imagine that I operate a farm and I grow crops, and those crops, the productivity of those crops depends on how much rainfall occurs. So it depends on the weather. But the productivity of my farm also depends on pollination and pest control services that are provided by wild species in the environment. So ecosystem services. If in this case, climate changes and the climate becomes drier, this not only affects the amount of water that's available for my crops, but also potentially the abundance or distribution of these wild species. And so in this sense, climate change could be affecting these non-weather inputs to production that farmers have no ability to control. And so the approach that we develop has a couple of benefits related to these channels. First, similar to other efforts to quantify the impact of climate change, we're going to be able to look at marginal impacts of climate that are net of potential adaptation. And this is sort of the policy relevant measure of climate impacts. Second, and critically, we're going to be able to distinguish climate impacts that come through this first channel, this sort of intuitive weather patterns channel, versus those that come through this non-weather channel, which has to date been understudied. And finally, another benefit of our approach is that we'll also be able to look at change in higher moments of climate, for example, the effect of changes in the standard deviation of the distribution of weather, as opposed to just mean shifts. So here's an example of data that we use in our empirical application. Our measure of economic or outcome of interest, in this case, our measure of agricultural productivity is net farm income per acre as measured in the US agricultural census. And our two weather variables of interest are measures of moderate and extreme heat exposure throughout the agricultural growing season. These are standard measures that are used in a lot of agronomic studies that are referred to as growing degree days and killing degree days, respectively, where the killing degree days refers to the fact that extreme heat exposure above a certain threshold has been shown to have negative impacts on crop productivity. And so then this slide shows an example of the kind of empirical results that we generate when we apply our methodology to these data. On the left, I'm showing the effect of a unit shift in the mean of the distribution of these extreme heating days, these killing degree days, on net farm profits per acre in each US county. And so the main takeaway from the left side of the figure is simply that in the vast majority of counties, in fact, in all counties, it looks like increasing the mean of the distribution of killing degree days has a negative impact on farm profits. The right side of the figure exemplifies the sort of novel contribution of our method and shows the share of this overall effect that comes through the sort of preliminary, the sort of intuitive future weather patterns channel that I discussed on the previous slide. So the numbers in panel B represent the share of the overall effect shown in panel A that results from a change in future weather patterns. And on average, this share is only around 11%. And so that implies that around 89% of the overall effect is actually resulting from climate-driven adjustments in these non-weather factors. And this is a new result and a surprising one from our standpoint, and suggests that there may be different ways to think about climate impacts and responses to climate impacts that focus on the sensitivity of economic activity to things like ecosystem services or environmental goods versus just the impacts of weather and changing weather patterns. Okay, and to close out, I'd like to talk about my third chapter, which focuses on the organization of industrial activity in the palm oil processing sector in Ghana. So for just a little bit of background, oil palm is a tree crop that produces woody fruit-bearing bunches called fresh fruit bunches about every 2 to 4 weeks once it is fully mature. And using the fruit from those bunches are stripped off, and the sort of fleshy bits of the fruit are cooked up and mashed and pressed to produce what's called crude palm oil, which is either used directly or further refined to produce a wide variety of products, including soaps, processed foods, consumer goods, and in West Africa, palm oil is also used in local cuisine, so directly in food preparation. And the development context for palm oil, which I'm sure many of you are aware of, is that the production of palm oil has increased dramatically over the past 50 or so years, primarily driven by the expansion of large plantations and plantation-based producer processor systems in Indonesia and Malaysia. And research on palm oil in this part of the world suggests that expansion of plantations has produced pro-poor economic growth in these countries, but is also obviously associated with large-scale environmental impacts, including deforestation, carbon emissions, and biodiversity loss. But partially as a result of the existence of economic benefits, there has been interest in promoting development in palm oil in West Africa, where the crop grows natively. So in Ghana, there are two types of palm oil processors. There are what we refer to as industrial processors that use large-scale machinery and sophisticated industrial equipment to process large quantities of fruit. And these are shown, the sort of 11 or 12 industrial processing facilities in Ghana are shown as blue triangles in the map on the left here. The second type of processing facility in Ghana is what we refer to as artisanal mills. These are the mom and pop shops of palm oil processing. They are small scale operations where an abundance of manual labor is used in combination with relatively rudimentary technology to produce, to process palm fruit into palm oil. And the map on the left here shows the count of operational artisanal mills in each district in Ghana's southern oil palm belt. So you can see that there are hundreds of these things in some places. Okay, so a key question that motivates our analysis is, why is the majority of palm fruit in Ghana processed by artisanal mills when they produce less oil per unit of fruit? The figure on the left shows the share of national palm oil production that is produced by artisanal and industrial mills, respectively. So not only do the artisanal mills produce more than the industrial mills, but if anything, it looks as if their share of aggregate national production is increasing over time. And on the right, the figure on the right shows a measure of the efficiency with which these different types of processors are able to convert palm fruit into palm oil. So in particular, the oil extraction rate measures the kilograms of crude palm oil that are obtained from processing 1 kilogram of palm fruit. And for artisanal mills, this extraction rate is usually between 12 and 15%, whereas for industrial mills, it ranges from about 18 to 25%. So again, this is sort of puzzling. Why is so much of the palm oil in Ghana produced at artisanal mills when you could use the same amount of fruit and get a lot more oil if it were processed at industrial mills? And there are a wide number of theories that could definitely apply to explain this phenomenon. Some of them, for example, it could be the case that missing markets for market frictions or missing markets, such as in land markets, prevent industrial mills from purchasing land from smallholders and developing dedicated plantations. It could be that a lack of resources in the Ghanaian government prevents them from effectively regulating and taxing artisanal mills. And so by virtue of operating extra legally, these mills have a comparative advantage relative to industrial processors. It may also be that there simply isn't sufficient demand domestically within Ghana for the type of refined industrial palm oil products that industrial mills produce. And so this lack of overall economic development creates a sort of dual economy where artisanal mills supply relatively low-grade palm oil to the domestic market, while industrial mills supply higher-grade products to the international market. Again, all of these theories potentially explain some share of what's going on in Ghana, but an important characteristic of all of these different explanations is that they generally predict that artisanal mills should disappear as economic development proceeds in Ghana. That is, as market frictions are decreased and missing markets come into existence, as institutions in the Ghanaian government become better resourced and the overall demand for industrial products in the country increases, we should see industrial mills replace artisanal mills in the trajectory of agricultural development. In this paper, we offer an alternative theory, namely that the hybrid composition of the palm oil processing sector instead reflects the impact of climate on the geography of industrial activity. So in particular, climate-driven seasonality in oil palm yields is one of the main differentiating features of West African oil palm systems relative to those in Southeast Asia. And so the argument we're going to make is that under seasonality, artisanal mills can actually complement industrial mills in order to increase the aggregate efficiency of the processing sector. And to do this, we're going to study a simple spatial model of facility location for a capacity constrained firm sourcing inputs from the local environment based on models recently proposed in the operations research literature, as well as canonical models of economic geography and spatial competition. So our model starts with a simple one-dimensional environment, just a line. And within this environment, a central planner can convert land into oil palm at a unit cost C. Land that is converted into oil palm produces palm fruit in 2 different seasons. So in the peak season, each unit of land produces a higher quantity of palm fruit, represented by the thicker green line, whereas in the lean season, each unit of land produces relatively less palm fruit, represented by the thinner green line. And then within this environment, our central planner is going to choose what type of palm oil processing facility to construct in order to convert palm fruit into palm oil. And in particular, the central planner's technology choice, we're going to define it in terms of this index N, where the social planner's choice of N determines 3 features of the processing technology. First, it determines the capacity of the mill. So how much palm fruit the mill is able to process in a particular season. And given the differential productivity of land in the peak versus lean season, we can represent this capacity in terms of capacity constraints, which are shown by black bars in this diagram. So these black bars indicate the size of land, which if the mill were to process all of the fruit grown within that interval, it would be operating at capacity. So note that because land is differentially productive in the peak versus lean season, these capacity constraints are located at different locations. The second thing the technology choice determines is the profit margin of the mill. So how much revenue or profit it earns on each unit of palm fruit processed. And finally, the technology choice also determines the fixed costs or capital costs that are required to construct the mill. We assume that all of these components are increasing in N. So the larger technologies have higher capacity and larger profit margins and also higher fixed costs. So that's meant to be represented by the size change in, in these two slides here. Okay, the final ingredient in our model is transportation costs. In particular, we assume that transporting 1 unit of palm fruit, 1 unit of distance, incurs a constant transportation cost tau. And these transportation costs imply an additional set of constraints, namely the mill will never source fruit from a location that is so far away, such that it costs more to transport it to its location than the profit margin it earns on processing it. Okay, so given this setup, we can think about the social planner as trying to maximize the profits earned by this industrial technology conditional on these constraints. And in particular, the social planner is going to choose how to operate this mill. The social planner is going to choose 4 things. It's going to choose how much land to develop, that's X. Going to choose what technology to use, that's N. And then also how to operate the mill. So how the size of the supply interval from which to source palm fruit in the peak and lean season, represented by XH and XL respectively. And if we put all of this together, we can represent the total profits earned by this firm using the equation written here. And it's worth noting that we can also write this as a formal optimization problem where the central planner first optimizes over the supply intervals and land development choices, conditional on the technology choice, and then optimizes an outer optimization problem over the technology choice. Don't need to get into the details here, but the point is that we can write this as a formal optimization problem, and it's a really interesting one. And so the first result that we get when we look at the optimal solutions to this problem are that when there is no seasonality, we get a solution that looks like this. A single optimal technology processes all of the palm fruit that is produced on the optimally sized interval of oil palm land. So there's no room for anything else. The industrial technology simply processes all of the fruit. By contrast, when we introduce seasonality for a range of values for the transportation cost parameter tau, the industrial mill becomes capacity constrained in the peak season. And this produces regions of unused palm fruit. So in general, the mill is able to use land less efficiently in the presence of seasonality, this optimal single technology. And so our final and sort of core theoretical result in this paper is that if we allow artisanal mills to process the fruit that is on these unused pieces of land in the shoulder season, that this hybrid configuration of the processing sector in fact produces more welfare than the optimal single technology by itself. So artisanal mills can complement industrial mills in the presence of seasonality. So to conclude, we show that in a simple spatial facility location model, seasonality creates an efficiency basis for artisanal mills. And critically, this argument does not rest on the existence of market failures or frictions in order to support the existence of artisanal mills in the supply chain. In addition, it's worth noting here that we support this theory empirically with data from an original survey that I don't have time to talk about. Okay, and to conclude, this project generally suggests that climate can affect the efficient spatial organization of industrial activity and highlights the need for applied development initiatives focused on oil palm in West Africa to account for the complementarities between artisanal and industrial mills. And I think with that, I am out of time, so I will stop. Thank you very much, and I look forward to your questions.
Thank you very much, Casey. You did well, but you budgeted your time very well. We have, at this point, 4 questions that have come in for Q&A. Actually 3, one had 2 parts. So let me read the first, which is from Noah Lincoln, and feel free to respond. Noah's question: the productivity measure starts from the assumption, and I guess we're talking about the very first chapter, that less people working in agriculture is a good thing. I'm wondering what your thoughts are about this. Often reduced labor in agriculture, while beneficial from a purely Western economic perspective, is associated with increased inputs, mechanization, environmental impacts, loss of cultural traditions, decrease in biocultural relationships, and so on and so on. The point being, there are infinite ways to define productivity depending on the values from which that productivity is defined. So I think the question is, what can you say about the productivity measure and the implicit definition of productivity?
Yeah, it's a really good point. I mean, I think Noah really said it. There are a lot of different ways to think about productivity. This notion of total factor productivity is one that is really important in the economics discipline, and one that has been studied a lot to try and understand both how productivity dynamics within an industry contribute to aggregate economic performance, and also to understand the process of economic development over time. And so, the reason for choosing TFP as a basis for evaluating productivity in this paper is really to try and speak to that literature. But I think the broader point that there are lots of different ways to measure productivity, and perhaps we would reach different conclusions if we were to use different measures, is totally valid.
Great, thank you. Now, 2 questions about chapter 2, the first of which is from an anonymous attendee. Asked, could you dive into more details about the pathways through which killing degree days indirectly impact farm income, and offer your thoughts on adaptation responses?
Yeah, so I think, well, I guess try to be succinct in this. We know that temperature exposure affects plant productivity directly from agronomic studies. So plants just tend to do less well when it's really, really hot. We also know that that climate more generally could affect lots of other aspects of the natural environment. So I think the point that we're trying to make in this paper is that it's not just the way that climate change affects weather variables such as temperature that have a direct impact on output in agriculture, but also the way that it affects the broader production system. And that includes sort of non-weather dimensions such as ecosystem services, such as other environmental goods. One example that we thought about a lot in this work is that characteristics of soil productivity, for example, may be determined by the average amount of rainfall in a location over the very long run, but are not meaningfully affected by how much rain falls in one particular year. So that's just one example of a sort of non-weather factor that could respond to a long-run change in climate. But specifically related to killing degree days, I think the literature in the agronomy literature suggests that that has a very direct impact on crop productivity.
So this next question, also about the same chapter, is by Miyuki Hino. And basically it's pretty much a similar question, so you can decide how brief you want to be here. But Miyuki is asking, can you hypothesize about what mechanisms are causing the 90% of the quote unquote indirect effects in the chapter?
Yeah, no, that's the $1 million question. like I said in the presentation, I think an important contribution of this work is simply to raise the possibility that this type of channel could be important. I mentioned that there could be indirect effects through things like soil productivity, through ecosystem services. There could also be ways in which our simple application of this method that we propose misattribute other factors to this indirect source. So, for example, if there are other dimensions of weather other than growing and killing degree days that have direct impacts on crop productivity, but we're not sort of using our method to model the weather effects of those other dimensions of weather explicitly, that may end up getting captured in this sort of indirect channel. So I think there's a lot of interesting future work to be done looking at sort of specifically theorized mechanisms that could operate in this way, and trying to do a better job of empirically of controlling for potentially unwanted factors. But like I said, raising the possibility that this channel is important is an important contribution of our work.
Okay, and we have one final question here, again by an anonymous attendee. The question is, can you talk a bit, and it relates to chapter 3, can you talk a bit about how the survey supplemented in your chapter 3 findings?
About so man, you know, it's such a hard thing to talk about all of this work in just 40 minutes. The survey was a really amazing experience. We surveyed 300 oil palm farmers in the Juaben region of central Ghana, specifically to understand how they make decisions around selling palm fruit to either industrial or artisanal processors. And one of the interesting things that we find in looking at that survey data is that farmers tend to sell their fruit to processors that are more geographically proximate to them, which makes sense. But this is sort of like, I'm more likely to sell to a processor who's close by than one who's far away. And this empirically supports the sort of way that we represented transportation costs in dictating the efficient size of the supply intervals in our theoretical model. Another thing we can look at is how farmers change who they sell to seasonally. So our core theoretical result is that in the presence of seasonality, there's these sort of shoulder seasons where palm fruit is not processed by the industrial processor. And if that's the case, then we would expect to see farmers who are located relatively far away from an industrial facility switching from selling to an industrial plant to an artisanal mill from the lean to the peak season. And that's also something that we see in our survey data. So both of those two things provide empirical support for the model representation.
Well, thanks. You've answered all the questions that came in at this point. We're doing well on time. So this will conclude the Q&A, or this will conclude the public portion. And I want to remind the attendees that they should feel free to offer comments, congratulations, etc., to Casey later on, but we won't be having a sort of a group gathering at the end. Also then, I want to indicate that I hope the other members of the committee will appreciate this. I'd like to suggest we have a 5-minute break and reconvene in 5 minutes to start the private session.
I think I'm going to do the acknowledgements before we break, Larry.
Oh, I'm sorry. I ignored that. Go ahead.
Yeah, no problem. Okay, so let me just reshare my screen. Move to the next slide. Okay, yeah, so when you're a graduate student for as long as I am, I've been in this program for going on 7 years now, you accumulate lots of people to thank for all the research that was done and progress that was made. So many people have made this dissertation possible. I'm so grateful to all of them for the friendship that they provided and also all the sort of meaningful help with research that I got through these different relationships. So I won't have time to thank everybody on this list, but I for sure wanted to give a huge thanks to all of my committee members. I had I think, relatively unique experience in this program of being able to work very deeply with each and every one of my committee members. And I have a committee of five advisors. So that's a lot of people. And I learned so much from each and every one of you. And I'm just so grateful to have had that opportunity. So just to say a few things in particular, Roz, you have been an inspiration to me to think about agriculture and economics since my days as an undergraduate student at Stanford, and the importance that you place on understanding the on-the-ground context and lived experience of people and individuals in the context that we study is something that I'll always carry with me. Charlie, you were the one, I think, more than others who really taught me how to think like an economist. And I'm so grateful to have had your wisdom and experience in thinking about how to orient myself as an interdisciplinary scholar and how to translate my interdisciplinary interests into meaningful and impactful economics research. Marshall, I think I learned the most from you about just how to do research in practice. It's been such an amazing experience learning about how you set up the research machine that you operate. And in addition, the excitement that you have for translating the work that you do into real world impact is also something that I'll always carry with me. And Erica, your enthusiasm and unbridled enthusiasm for learning and doing research is truly infectious. And I think I learned from you that if you're just optimistic and stay interested and excited about what you're doing, that anything is possible. And so I'm so grateful to have had the opportunity to work with you. And finally, Kyle, your willingness to work with me from afar over at Tufts indicates just how gracious and you have been with your time and extending your advice and expertise to me as I learned how to do the project that we were working on is something that I'll always be grateful for. So thank you so much for listening and helping me develop as a student, even though that was outside of your job description. Just super quickly, I want to thank all of the sources of funding that I've had over the course of my 7 years here, all of the great research assistants who've worked with me on all of my different projects, and all of the different students in the E-IPER community, in the economics and MS&E communities, and in the Burke lab, who have really supported me and helped me develop as an intellectual and scholar. And finally, I just want to thank my friends and family. I would not be here without them, and in particular, Kika and Marty, who really kept me going this year. Oh, I actually want to go back and give a special call out to the E-IPER staff. I forgot to do that. These guys keep my world running. I'm not the most organized person, and these guys have made this process go off without a hitch, and for that, I'm extremely grateful. And in particularly to Anne-Marie Pettigrew, who I think took a special interest in making sure that I was healthy and happy as a student during my time here. So thanks very much to Anne-Marie. And with that, yeah, I'll close things off. So thanks again to everyone.